Hello friends and welcome to the second lecture of Module 5 in which we'll discuss the analysis of hydraulic jump. So our learning objectives are that we'll apply the momentum equation to study the hydraulic jump phenomena. In the last lecture we saw that the energy equation is not sufficient to get insights about this hydraulic jump phenomena, and that is why the momentum equation is necessary. Then we'll study the characteristics of hydraulic jump in a rectangular channel, that what are the sequent depth ratio, energy loss, relative energy loss, and other characteristics. And then we also last time discussed the uses of hydraulic jump, in which the very prominent use was energy dissipator. So through a real world case study, we will demonstrate that how the hydraulic jump is useful in energy dissipation. If it not achieved, then what can be the consequences. So we begin with the momentum equation formulation for hydraulic jump. So we apply the linear momentum equation in a longitudinal direction into the control volume. So the linear momentum equation becomes P1 minus P2 minus Fs plus W sine theta, that is equal to M2 minus M1. So this is the control volume. So in this control volume, this is the depth y1, that is the supercritical depth, y2 is a subcritical depth, and this is the hydraulic jump which is being formed. So at this we have a hydrostatic pressure again here, and in between the pressure distribution is different from hydrostatic because there is excessive curvature. So the W is a weight which is acting in the downward direction. We take W sine theta component in this longitudinal direction, and opposite to that we have Fs, that is a shear force component. So the pressure force acts as a CG of the cross section, which is located at the depth y bar from the free surface, and the total depth of flow is y. So your initial y1 that corresponds to E1, and that is y1 plus v1 square by 2g, and the y2 here corresponds to E2. Now you may wonder that for the same E1 you may get y1 and y2. So that particular depth y2 dash, I'll call it as an alternate depth. But in case of a hydraulic jump, there is an energy loss. So this is your energy loss EL, and thus the energy is lost while attaining this sequent depth y2, and that is why it has a different energy. So E2 is E1 minus EL. So there is an energy loss. So that is the transition in hydraulic jump being represented using this specific energy diagram. So going back to our equation, so just understanding the equation, so we have the pressure terms at the control surfaces. So that is a hydrostatic distribution. So it is gamma 1 A1 y bar by 1 bar cos theta, and similarly gamma 2 A2 y2 bar cos theta. Now the shear force term. Now in case of RVF, the boundary friction is negligible. So usually this shear force is neglected when we talk about RVF. Thus, if we consider horizontal channel, the sine theta component, that theta is 0, so sine theta becomes 0, and this component also disappears. And M2 and M1 are the momentum flux which are entering and leaving the control volume, which are given by beta, rho, Q, and V. So using this equation, we move forward and we derive the relationship for a hydraulic jump in a rectangular channel. So in this, we consider a horizontal frictionless rectangular channel, and the channel is of unit width. So applying the momentum equation and rearranging the equation 1, we get half gamma y1 square minus half gamma y2 square, that is beta 2 qv rho q v2, that is discharge per unit width small q, minus beta 1 rho q v1. Now let us consider your momentum correction coefficient is equal to 1, and applying continuity equation. So on subsequent substitution and rearrangement, you come down to this equation, that is y1 y2 into y2 plus y1, that is equal to 2q square by g. So okay, so this is simple mathematical substitutions. Now we divide this equation 3 throughout by 2y1 cube. because we want to find the relationship between y1 and y2. So what is the sequent depth relationship? So that we want to know. So when we divide it by 2y1 cube, we get to this form, that is half y2 by y1 into 1 plus y2 by y1 and q square upon g y1 cube. Now we know that Froude number is given by v upon under root gy. We square it, it is v square upon gy, and using the continuity equation and modifying it, v is nothing but q by y. So this part can be substituted as f1, that is the Froude number of entering flow, and thus solving this equation 5, it yields y2 by y1 is equal to half into brackets minus 1 plus under root 1 plus 8 f1 square. So this is a very important equation. This equation relates the sequent depths or the conjugate depths to the initial Froude number. Now, if you solve this equation for y1 by y2, you also yield the similar form, but only thing is it is in terms of f2. So these two forms of the equation are very helpful in solving any problem of hydraulic jump. So after this, we have also seen there is energy loss in the hydraulic jump. So let us derive how the energy loss is computed. So as seen from the previous specific energy diagram, your energy loss EL is the difference between the energies in section 1 and 2, that is incoming and outgoing flow. So it is E1 minus E2. E1, you know that by applying specific energy concept, it is Y1 plus V1 square by 2G, and similarly E2. So on solving, you get a form where it is y1 minus y2 plus q square by 2g into y2 square minus y1 square upon y1 square y2 square. Now this is something familiar. So in equation 3, I'll just go back to the equation 3 where we had 2q square by g. So we have this relation q square by g, and this 2 will come on the LHS side. So using this equation 3, we will substitute in equation 8, and if you do some mathematical simplification, so you will get an answer in the form of a minus b the whole cube. So that expansion can be applied here. So EL is the difference of y2 minus y1 the whole cube upon 4 y1 y2. So the energy loss in the hydraulic jump is purely dependent upon the pre-jump and post-jump depth. So y1 is a pre-jump depth and y2 is a post-jump depth. There is another term called relative energy loss, which is the ratio of EL by E1. So your earlier energy is E1 and your final energy is EL. Sorry, energy loss is EL. So using that, we find out what is the relationship between EL and E1. So as we simplify it, EL by E1 is nothing but EL by Y1 upon E1 by Y1. You just substitute all the values, then you get the simplification done, and once you solve this equation, you will finally have expanded form, that is EL by E1 is 8f1 raised to 4 plus 20 f1 square minus 8 f1 square plus 1 raised to the power 3 by 2 minus 1 the whole divided by 8 f1 square into 2 plus f1 square. So understanding this equation, how the relative energy loss is related. So a small graphical representation can be seen here. So let us say you have a Froude number. So this is the curve. So if you substitute the value of F1, then you get the relative values of EL by E1, and you plot at all levels, you get this curve. So you can see the maximum energy loss relative to your original energy, that is somewhere around 86%, that is available in your Froude number is maximum, that is 20 we have considered. Okay, so it is very difficult to achieve such high Froude number, but we are assuming that we are considering that high Froude number. Now let us take Froude number equal to 5. So at this Froude number, your EL by E1 is 50%. So that means half of the energy is lost at Froude number equal to 5. So this curve is very useful in designing the energy dissipation devices. So let us say if you know the Froude number, or if you have a target in mind that you want to reduce 80% energy or 60% energy, then you can just backtrack on this and okay, Froude number of 8 is required, so thus you can create those flow conditions. So that is why this curve is very important. So let us look further characteristics of the hydraulic jump. So how the length of a hydraulic jump is defined. So length of the hydraulic jump is from this point to this point. That is the length. And if we look in the vertical direction, the difference is the height of the jump. So it is a very important parameter because as I discussed in the previous lecture also, if your length of the jump is too high, then you require that much size of the stilling basin to contain the jump on the concrete floor. So that is why the length of jump. So usually you can see it is a variable with respect to Froude number, but based on several empirical studies, they have given that length of jump is 6.9 times y2 minus y1. So y2 minus y1 is the height of jump. So if you know the height of jump, just multiply by 6.9 and you get the um, length of jump. Another relationship is that with respect to your y2 also it can be approximated that it is 6.1 times y2 if your Froude number is greater than 4.5. So that is another approximation. Now there are some curves which are called characteristic curves of hydraulic jumps. Now these are valid for jumps in a horizontal rectangular channel. If you change it to a sloping rectangular channel or any other cross section, the same curves are not valid. You have to derive different curves. So what are the quantities it is representing? It is representing E2 by E1, that is ratio of the specific energies, Hj by E1, that is height of jump divided by initial specific energy, Y1 by E1, that is initial depth of flow divided by the specific energy, and Y2 by E1, that is a post jump depth divided by E1 versus all values of F1. So if we look at this curve, this Y1 by E1, it decreases with the increase in Froude number. The curve Hj by E1, it increases till a point that is around 2.77 and then it decreases 2.77 of Froude number and then it decreases. Similarly, the curve Y2 by E1, it increases till Froude number is 1.73, then it decreases back. And the last curve, that is E2 by E1. So the residual of this curve, so whatever is above this curve, that will give you the delta E by E1. So you have this delta E by E1, that is the change in energy or the energy loss divided by the initial specific energy. So it is the relative energy loss. So this curve is very important when you design the structure for a range of condition to which it may likely be encountered in the field. Now the last part is in the characteristics, is the second last part, is the velocity profile of a jump. So how a hydraulic jump uh, occurs. So what is the velocity? So if you see this diagram, so the velocity distribution might appear to be something different than what you see in an open channel. You have two portions, one is a reverse flow, one is a forward flow portion. So this is a part where your eddies are generated in the upper surface rollers. So there the flow reversal takes place, and due to that the velocity this is on the negative side. And here this is a forward flow which is happening in the forward direction. So uh, the top surface of the high velocity flow will have high relative velocity with respect to the fluid mass that overlays it. Now the boundary shear will cause the retardation of velocity in a boundary layer. So there are two different portions where there is a forward flow and there is a negative velocity region in the top which is called the reverse flow. So in forward flow, there is the discharge which is in the jump, so that is due to the flow entrainment in the shear layer. Now if you want to maintain the continuity, so the excess to account for the excess flow which is there in the forward flow, a reverse flow exists at the top, and this situation results in the formation of rollers. So thus the velocity distribution in the hydraulic jump can be idealized in this particular manner, wherein in the forward flow also there are two ranges. In the initial range where your flow depth is between 0 to delta, that is a boundary layer region where at which you're at y equal to delta, your velocity is maximum, and in the region above that from delta to yf, so in that is called the free mixing zone. So there are two zones being delineated in the forward flow region. Now you can also find what is the water surface profile of the jump. So this is the point where your jump starts. So that can be idealized at 0 0 in the coordinate system, and based on that you can take, this is the h direction in the vertical and x in the horizontal. So two scales are defined, and this is the hydraulic jump. So where it ends, this is your length of jump, and this is y2 minus y1, that is the height of the jump. So the water surface profile can be idealized by this relationship, where eta is equal to h upon 0.75 y2 minus y1, where eta is a function of lambda, and lambda is small x by capital X, where capital X is a length scale at which the value of x is 0.75 into y2 minus y1. So at this point, initial point, just before that, your pressure distribution is hydrostatic, but during the jump your pressure distribution is less than the hydrostatic pressure, and the water surface profile will represent the pressure head profile. So this is how the pressure head can be found. So when you are designing hydraulic jumps and you want to find what is the pressure at different points, the profile is very important to understand that pressure variation, and it can be easily calculated using this relationship. Now, the last part of this lecture, we identify the role of hydraulic jump as an energy dissipator with a real world case study. So this case study is published as a Springer book chapter. So the details are also given here. So the title is Identification of Causes of Failure of Downstream Block Protection of Singanpur Weir Cum Causeway in Surat. So this was a Weir Cum Causeway. So causeway is a low-lying structure over which the vehicle movement is allowed. However, in case of high flows in the river, the vehicular movement is stopped. So this is in Surat. The problem background is that it was constructed in year 1995, but in the year 2013 and 14, the weir is comprising of three portions. So significant damages were observed in the downstream portion of the weir, and it got damaged. So the study is based on the causes to identify what led to its damage, and some remedial measures were also being proposed. So if you want more details, you can refer this publication. The link is also provided. So it is also available in the ResearchGate, and also you can request the author also if you want a copy of it. So we identify the causes why that failure occurred. So if you look at the picture, so this is a picture taken somewhere in around 2017 or so, when this study was conducted. So you can see that in a weir, so this is the concrete portion, and these are the end sills which are meant for the flow, raising the flow to some extent so that in the stilling basin. So this part is the stilling basin, and from the upstream of this there is a weir portion which is there, and in the downstream this was the concrete block protection. So in the concrete block protection, what happens, that it is because it is a weir, so it is created on a permeable foundation. So in the concrete block protection, the concrete blocks are arranged, and if there is some scouring below it, the launching apron at the end will launch itself so that the scouring is stopped. So you can see that from the original level here, this much subsidence has taken place in the concrete blocks. Okay, so that has damaged the structure, and the displacement of concrete blocks from its mean position has caused a lot of damage, and we have to investigate it. Now this structure is also unique in the sense that on the upstream of the structure there is Tapi river which is flowing, in the downstream the tidal waves from the Arabian Sea are hitting the structure. Okay, so what we did, we tried to analyze the hydraulic jump condition. So the maximum discharge, that is the design discharge, was 24,000 meter cube per second, and we went on till the minimum of 2000 meter cube per second discharge. For that we computed what is the high flood level and what is a discharge, because it has two arrangement that discharge goes over the main weir and through the sluice gate also. And doing some other basic calculation, what is the head loss. So you can see that the head loss is also computed, that at higher discharge the head loss is less, and the lower discharge the head loss is more. So that is also computed. The difference between pre-jump and post-jump also, you can see the depths also can be computed, and the tailwater depth is also obtained based on the conditions in the downstream. So what we found that on the concrete blocks, whether the hydraulic jump uh, occurs on the concrete block, that is, it is a free jump or it is a repelled jump. So our question is whether repelled jump forms on the concrete block and launching apron. So till the discharge of 4000 meter cube per second, the answer is no, that the hydraulic jump, there is no repelled jump formation. There is a jump at vena contracta, or what we can say a toe of the weir, or it is contained within the stilling basin. But for discharges less than 4000, a repelled jump was formed. Now this is a critical condition. If a repelled jump is formed, we have to identify what is the length of that jump, because the energy is not dissipated till the jump is formed. The repelled jump is a GVF profile. So using the Chow's method, we calculate the profile length, and we found that in this case, for the discharge 3000, the length of GVF profile was 62 meter, while in 2000 meter cube per second discharge was 92 meter. However, the actual length of concrete surface was just 27 meter. So around 35 meter here and 65 meter here, the jump was forming outside the concrete floor, and that was damaging the structure. So in this case, contrary to our assumption that okay, more flood is coming, it will cause damage, it is rather less flood magnitude is causing damage, because the energy dissipation doesn't occur. Okay, so that is the concept. So we can see graphically also, these profiles were plotted in AutoCAD and visualize. So if we see the profiles, the first one is for 6000 meter cube per second, where the hydraulic jump is forming on the glacis. So this is the downstream glacis. Their hydraulic jump is formed. But when we go for 3000 meter, the hydraulic jump is formed downstream. Even after this is the downstream concrete floor. This is the concrete blocks, and here it's somewhere launching apron. Crossing that, the hydraulic jump is formed. And for the that total length of jump including the GVF profile, that is 71 meter, and here the length of jump from the toe, that is 91 meter. This is the toe. So that is for 2000 meter cube per second. So you can see such conditions being observed, and that is responsible for the uh, scouring in the downstream. So what we propose is an alternate solution, that to shift the jump upstream, you should raise the downstream water level so that the jump is shifted upstream towards the glacis. So the suggestion was that this is the existing structure till the concrete floor of 27 meter. Below that you have concrete blocks, so that concrete blocks may be displaced and can be replaced by a downstream, that is a sloping concrete floor. So we are providing a 1 in 25 slope of the concrete floor, and this concrete will ensure that the hydraulic jump forms here, and the downstream loose protection is also provided, that is in form of launching apron. So ideally we want this situation that when the upstream water level comes, H3 profile is formed, then S2 profile, then a jump takes place, and S1 profile, and then it meets the tailwater level. So this is what we propose. Then we try to solve this and then design it. So we can see here the diagram shows two alternatives, that is for 2000 meter cube per second and 6000. 6000 was not problematic, so the new geometry is also shown. This is the concrete floor which is extended, then you have the concrete blocks and all. Now when we did for 2000 meter cube per second, so from this point at a distance of around 9.66 meter, the hydraulic jump was formed. So that means by lowering this, so this is RL 3 meter and this is RL 1. So by 2 meter, we are just lowering it, and we are trying to increase the downstream tailwater depth, and thus we are achieving the shifting of hydraulic jump in the upstream direction. and that is a solution being proposed from this study. So that highlights the importance of hydraulic jump and energy dissipation due to hydraulic jump. So with this, we complete the portion of hydraulic jump, and next we are going to discuss the unsteady flow. So thank you everyone and have a nice day.